We continue the lecture now. This is an example where we will have a Fourier series at the end of the solution. This problem represents a circular infinite cylinder. We want to find the temperature distribution inside the cylinder, given that the temperature U is equal to 0 on the outer surface of the cylinder with radius C. So at rho equals C, the temperature U is equal to 0. And also, the letter, we said that, the letter is okay. So we read the problem here. Also, the temperatures will depend only on the space variable rho. It does not depend on phi or on z. And also at time t. The material is homogeneous of the cylinder. The temperature U as function of rho and t only. It is not function of z or phi. In the cylinder satisfy the special case. Okay, this is the equation, differential equation. Okay, 1 over k du by dt, partial derivative of the temperature with respect to time, equal u rho, second partial derivative of u with respect to rho, plus 1 over rho, first derivative, partial derivative of u with respect to rho, where rho varies from 0 to c and time is greater than 0. The boundary conditions, the temperature on the outer surface, as we said, on the cylinder is equal to 0. The outer surface is characterized by rho equal to c for all times greater than 0. And the initial condition, U, the temperature at time 0, is a certain distribution as function of rho. F given function as function of rho, where rho varies from 0 to c. Okay. Now the solution, we apply the method of separation of variables. Okay. So we assume that the U is equal capital R as function of R and capital T as function of small t. Okay. So here, this is the assumption. This should precede this equation, should be the first step here, is to assume that U as function of, no, this is the initial condition. This like here, U as function of rho, okay, rho and t is equal as R as function of rho, function, a known function as function of rho times a known function as function of t. Okay, so this is the equation. Now we assume U as function of rho and t equal R as function of rho times t as function of t. Now substitute this in this differential equation as we did in the previous example. We will obtain, let me make this smaller to see both equations at the same time. Okay. Okay. 1 over k here, 1 over k. And here it will be t prime, and we divide, of course, this by u, which is r times t, we will obtain this t prime over t equal r double prime over r plus 1 over rho r prime over r. We did an example on separation of variables in the previous pages or in the previous lecture. We obtain this equation now. Now we want to apply the boundary conditions. U at the outer surface, rho equals C is equal to 0, which is equal, if you substitute here, rho equals C, and here, okay. Okay. So we cannot say that t as function of t as a function is equal to 0. So we say that r as function at c, at a function at a particular point is equal to 0. Not all the function, but the function at a certain point. Okay. So r at c is equal to 0. Now let's take, now since this function here as function of time only, and this function is function of rho only, they are equal, then each of them should equal to a constant parameter, we call it minus lambda. Because if we fix, for example, rho, and we vary t, if the function as if this term as function of t varies, then this means that the equality does not hold anymore, which is not correct. So both of them should equal a constant minus lambda. And the same can be said about rho, and the same can be said about t. Now, if you take this equation to the right-hand side, if you multiply by r, okay, or equation by r, and by rho also, we will obtain rho times r double dash plus r dash only here, plus, if you take minus lambda to the left-hand side, it will be plus lambda, and we have multiplied by rho and capital R equal to 0. This is a differential equation, but it is ordinary differential equation with variable coefficients, because we have rho is variable. The other equation, which is t prime over kt equal minus lambda, if you multiply by kt and take minus lambda to the left-hand side, the equation will end up with t prime plus lambda kt equals 0, like this, for t greater than 0. Now let's start to solve the equations. Okay. This equation is Legendre polynomial. This is Legendre polynomials equation, and the equation is well known, where the eigenvalues lambda is equal alpha j squared, j equal 1, 2, 3, etc. And alpha jc are the roots of the equation. So j naught of alpha jc equal to 0. Okay. Are the roots of this equation. This is Legendre's polynomials. J0 of order 0 at alpha jc equal to 0. Because at C, the temperature is equal to 0. And Rj equal J0 as function of alpha j rho, of course, in general, are the corresponding eigenfunctions. So this is the eigen roots or eigen values here, alpha j, and the eigenfunctions are J0 as function of alpha j rho. Now let's consider the other equation, t prime plus lambda j kt is equal to 0, where of course we have already found that lambda j is equal alpha j squared from here. Now this is a simple differential, ordinary differential equation with constant coefficients, and the solution is very easy. Tg equal exponential minus alpha j squared kt. Okay, k is a constant, alpha j is constant, and t is the time. We do not put a constant here because in the summation we will put the constant later on. Now uj, because this is one mode of the solution, one mode, one single term of the series, is equal rj as function of rho times tj as function of t. And j is variable, of course, because j represents or is the index of the eigenvalue and eigenfunction. Now rj equal j0 as function of alpha j rho, and tj from here it is equal minus alpha j squared kt, where j equal 1, 2, 3, etc. This is one single solution, one single mode. Now the total solution is the summation of these modes, summation for j equal 1 to infinity, aj constant times j0 times exponential. Okay. To find aj, we apply the initial condition that u as function of rho and at time 0, okay, at time 0 is equal f as function of rho, which is given already. Now, if you put here time 0, this will cancel, and we have summation aj j0 alpha j rho. This is a valid Fourier Bessel. Sorry, this is Bessel functions, not Legendre. Sorry, this is Bessel functions, j0, not Legendre. Okay, this is a valid for a Bessel series representation if the coefficients aj have the values. Okay, aj is equal 1 over j0 as function of alpha j rho magnitude squared integration from 0 to c rho f of rho j0 as function of alpha j rho d rho. Here the weighting function is rho for Bessel functions. It is rho. The weighting function is rho. So this is magnitude squared as we, this is generalized Fourier series, magnitude squared, and here the weighting function is rho, and we take the function times multiplied by one of the Bessel functions, alpha j as function of rho, where j0 as function of alpha j rho squared is equal c squared over 2 times j1 as function of alpha j c squared. This is identity from Bessel functions. And aj is equal to, we substitute for the magnitude squared here in the denominator here to get this equation here, 2 over c squared j1 squared. Okay, integration from 0 to c here, rho f rho j0 0. And the final solution is this. We substitute the coefficient here aj in the summation here, just to substitute to obtain the final solution. So this is the final solution, 2 over c squared integration j0 alpha j rho over j1 squared exponential minus alpha j squared kt. This is from the coefficient integration from 0 to c s f of s. We did not put here rho because we do not want rho to appear both outside and inside the integration. So we put an arbitrary variable s instead of rho as function f of s j0 alpha j s ds from 0 to c. We finished now the Fourier series. We start with the Fourier integrals and applications. Fourier integrals and applications. This chapter presents the trigonometry, which is Fourier transform. Is the same Fourier integral or Fourier transform. This chapter presents the trigonometric representations for functions defined for all x that are not periodic. The Fourier series represents a periodic function, even if the function is not periodic. If it is defined on a certain interval, then the series will replicate for all intervals of the same length of the same that has the same length as the original interval. So the series is periodic, whether we want or not. But here, assume that a function is defined for all x or for all time from minus to for all x from minus to plus infinity, or from 0 to infinity, for example. So here we cannot use we have to use the Fourier transform or Fourier integral. Now let f of x be a function defined on the piecewise continuous function from minus c to c. The corresponding Fourier series, I want to derive now Fourier transform from Fourier series, where I put here minus c and c, and then I will assume that c will go to infinity, or take the limit as c goes to infinity. F of x will be a0 over 2. This is the Fourier series, generalized Fourier series, or the Fourier series itself with cosine and sine. A and cosine n pi over c times x plus b and sine n pi over c x, and x from minus c to c. And we said that the frequency is 2 pi over 2c. 2 pi over the period is 2c, which is pi over c. And n here the index, and x or the number, integer, and x is the variable. Introducing the formulas for an and bn in this equation yields. Now let's put an and bn. Instead of an, we put 1 over 2c integration from minus c to c f of s ds. Okay, this is a0. This is a0 plus summation n1 to infinity. This is an 1 over c integration from c to c minus c to c f of s cosine n pi s over c ds times the cosine as it is here. So I put here inside the integral s instead of x, because we do not to have any confusion, plus bn. This is bn into 1 over c integration from minus c to c f of s sine n pi s over c ds, and this is the sign here as it is, sine n pi x over c. Okay, using the identity cosine a minus b equal cosine cosine plus sine sine, the right hand side integrals are written as, okay, so we have the constant here term as it is. We take it as it is. Okay, okay, and then we have f of x. This is the constant, and summation n from 1 to infinity 1 over c integration f of s. Okay, so this is if we take 1 over c integration from minus c to c here, f of s. Okay, if we take the cosine inside, if we put the cosine inside the integral, we can put it because it is in terms of x and the integral is in terms of s. And again here also similarly we we put the sign inside the integral. So we'll have cosine cosine plus sine sine. Okay, and this is common factor into 1 over c integration from minus c to c f of s, common factor. And this is cosine cosine plus sine sine is cosine, the argument of the first cosine minus the argument of the second cosine. It will be n pi over c s minus x, as you can see here, or x minus c. It is okay because cosine is an even function. Now we said that delta omega is equal to pi over 2c, which is pi over c. So 1 over c is equal delta omega over, if 1 over c equal delta omega over pi. Okay. So let's substitute delta omega over pi instead of 1 over c. So this is the first term as it is. And here, instead 1 over c, we put delta omega over pi. So it is delta omega over pi. And we put this as is. If we take the limit as c goes to infinity now, because we want Fourier transform, we said that we want f of x to vary from minus to plus infinity, to be defined from minus to plus infinity, not to be defined on finite interval or certain interval. So if we take the limit as c goes to infinity, this will go to 0, because it is we said it is f of x is piecewise continuous. So the integration the total integration will be finite. Finite over infinity will be 0. So this term will cancel. We will end up only with the second term. Okay. So now put here minus to plus infinity, minus c to c, it will be minus to plus infinity, as you can see. F of s times cosine n pi over c. Okay. We said pi over c is omega. Okay. Or delta omega, we said omega. Okay. N pi over c is delta omega, and n pi over c is omega itself. Okay. So instead n pi over c, we put omega instead of, as you can see, 1 over c is delta omega over pi. So delta omega is pi over c, and n delta omega, or n pi over c, is the omega itself. N delta omega is omega. So the equation will be like this. Now n from 1 to infinity, it will be, now we have ds and dw. W is from 0 to infinity, because this frequency from 1 to infinity. So it will be d omega from 0 to infinity, and ds is from minus to plus infinity. 1 over pi f of s cosine omega s minus x. Okay, we said here omega equal n delta omega. This might be expressed as f of x equal real part of, instead of cosine we put exponential, complex exponential j omega s times exponential minus j omega x here. So, the negative sign turns into multiplication when it is in the exponent part of the exponential. Okay. Since the integral is with respect to us, we take the x outside. We can't take the x outside term. Okay. Outside this integral. The term between brackets in the above equation is the Fourier transform of f of s. Okay. This is the Fourier transform of f of s, which is integration from minus to plus infinity f of s, or here 1 over pi f of s exponential j omega s ds. And the rest is the inverse integral. So we have here the inverse transform. So this is the transform. Okay, is the Fourier transform, and this is the inverse Fourier transform. We will end up with the same function because we take the Fourier transform and inverse Fourier transform. As you can see, the remaining part is the inverse Fourier transform. Returning to the real format and expanding the cosine term produces. Okay, real part of 1 over pi here, this equation. Okay, instead of exponential j omega s, we write cosine omega s plus j sine omega s. We want to take the real part. So it is cosine omega s, okay, here f of s, times cosine omega s ds, plus j 1 over pi, the same, minus plus infinity phi, f of s sine omega s. So it is cosine plus j sine omega s ds. Okay. Times here, this is also cosine omega x plus j minus j sine omega x. Cosine omega s minus j. So instead of exponential j omega s, we put cosine omega s plus j sine omega s. Instead of this, we write cosine omega x minus j sine omega x, as you can see here. Okay. Okay. I think all of this should be okay. So all of this are multiplied by this. Now, okay. Now this is the real part is integration from 0 to infinity 1 over pi from minus to plus infinity f of s cosine omega s ds times here the real part will be real times real minus imaginary times imaginary. As you can, if you multiply two complex numbers, okay, the real part of this multiplication, because we have here this complex number, as you can see, or complex quantity is multiplied by this complex quantity. So the real part, the net real part is real times real, real of the first times real of the second, minus imaginary of the first times imaginary of the second. So real of the first is this term here, as you can see. Okay. Real of the first times real of the second is cosine omega x. Here it is multiplied by cosine omega x. Okay. And the imaginary of the first is this 1 over pi from minus 1 gf of s sine. And the imaginary of the second is sine also. So we said minus will go with the minus. Because we said real times real minus imaginary times imaginary. And there is minus sign, it will be plus here. Which is, this is equal, it's called, this is cosine omega x, and this integral we call it, all this integration with d omega, of course, we call it a as function of omega. And this integral we call it b as function of omega times the sine. Okay? So a as function of omega is 1 over pi, integration from minus to plus infinity, f of x or s, no problem, x cosine omega x dx. And b here, integration from minus to plus infinity and 1 over pi, of course, f of x times sine omega x dx, or s, it is okay. So this is the Fourier integral. We have different cases. If f of x is even, as we said, as we explained in the Fourier series, if it is even, we multiply by 2 and take half the interval. So it is from 0 to infinity and multiply by 2. F of x, okay. Or here, if it is, no, here, sorry. If it is even, then sine the b of omega will be 0. And if it is odd, then a of omega is equal to 0, as we can see here. If it is even, okay, then it is the integral, the equation will reduces to the cosine term only. If it is odd, the integral will, the formula will end up with the sine term only, as you can see. If it is even, only the cosine, okay, here. If it is odd, then we will have only the sine. Yeah. F of x is defined on the piecewise continuous interval from 0 to infinity. Okay. Then the even extension of f of x is represented by a cosine integral. Okay. Likewise, the extension of f of x is represented by sine integral. The same, almost the same note as above. Observation, f of x defined on the piecewise continuous interval from 0 to infinity could be represented by either a sine integral or cosine integral. If it is defined from 0 to infinity, then if you assume it is even, use the cosine term. If it is odd, use the sine term. If it is defined from minus to plus infinity, then both sine and cosine will appear. And if it is, of course, not even or not odd. Applications, consider the eigenvalue problems. Here is here. X double dash ordinary derivative plus lambda x equal to 0, where x dash as 0 equals 0, okay, and x is positive, x greater than 0. and x value is less than maximum value. If lambda is equal to 0, okay, and x as function of x, then x is equal to x. Okay, let me see the original file. Okay, here, let me see here. Here B, here this is the Fourier integral. Okay, this is the case one. Okay. 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 Here we will have lambda equal omega squared, and the solution is simply x of x equal cosine omega x, because it is root lambda. We know that. All of the eigenfunction x of x equal cosine omega x, okay, have no orthogonality. This is not C, this is cosine. Cosine root lambda x. Root lambda x. Because the characteristic equation will be m squared plus lambda equals 0, m squared equal minus lambda. So m equal plus or minus j root lambda. So the solution will be cosine and sine, but here it will be cosine only because the x prime is equal to 0. So cosine here will be root lambda x. And here we take the lambda. Okay. This is cosine root lambda x. And root lambda is equal, we call it omega, so it will be cosine omega x. Although the eigenfunctions x of x cosine omega x have no orthogonality property, since omega is continuous, the Fourier cosine integration gives the representation of f of x for x positive, which are generalized the linear combinations of those eigenfunctions. Case 2. X double dash plus lambda x equal to 0, the same equation, but here x of 0 equals 0, not x prime. So we'll have the sign. Solution will be sine omega x. F of x is represented in terms of sine omega x through the Fourier sine integral formula, of course. There is an example here. This is an infinite or infinite medium, yes. We have x varies from 0 to infinity and y varies from 0 to infinity. This is the first quarter. A Laplacian or del squared of u temperature is equal to 0. And the temperature on the x-axis is given, okay, as a certain function, given function, which is f of x, okay. and also the temperature on the y-axis is equal to 0. We want to solve this problem to find the temperature distribution inside the region. Inside the first quarter. So let's put the Laplace equation, second partial of u with respect to x plus second partial of u with respect to y is equal to 0. And the boundary conditions are, of course, u is bounded. Boundary conditions, u at x equal to 0, which is the y-axis is equal to 0, as given here. And also u at y is equal to 0, which is the x-axis given function, which is f of x. Now, we assume that separation of variables, of course, we assume that u is equal capital X times capital Y, where capital X is function of only a small x and capital Y is function of only small y. We apply the separation of variables to obtain this equation here. From this, we substitute in this equation. We will obtain this using the same procedure. Derive u with respect twice with respect to x, twice with respect to y, and substitute them into the differential equation and divide the whole equation by capital X, capital Y. You will obtain this capital X double dash over capital X plus Y double dash over Y equal to 0. Now, if you take Y double dash over Y to the right hand side, it will be minus, and both of them should equal constant as we said before. So X double dash over capital X equal minus W squared, and Y double dash over Y equal W squared, because their summation should equal to 0. So minus W squared plus W squared is equal to 0. Now, if you solve this problem, you will obtain a solution, which is a cosine, of course, plus b sine as function of x. It is ordinary differential equation with of second order with constant coefficient. So it will be m squared plus w squared is equal to 0. So m squared equal minus w squared, and m equal plus minus jw, and the solution will be a cosine wx plus c sine plus b sine wx. Now we apply the conditions. X at x equal to 0, okay, which is the y-axis is equal to 0 given. So this will be a, b, the sine is equal to 0, and cosine equal 1. So this is a, so a should equal to 0, okay. So if we put here x as at 0 and y at y, as we said before, x, the function at one point is equal to 0. Not all the other function is equal to 0. So x at 0 equals 0. So should equal 0. And we have the function will be sine omega x. We do not put the constant because we will have summation or integration after that, and we will put the constant. Now y as function of y, okay. Now if you put this here, it will be positive. So m squared equal w squared, m equal plus or minus w. So it will be exponential. C1 exponential wy plus b exponential minus wy. One might ask, why did we choose the cosine and sine in the x direction and the exponential in the y direction? Maybe we can say that since the sources, the heat source here are on the x-axis, so we cannot put it, it will not decay to 0 as the x goes high. But here on the y-axis, there are no sources, so the temperature would decay to 0 in the y direction. That's why we put the exponential in the y direction to decay to 0 and the cosine and sine in the x direction. Okay. Now the y is equal exponential minus omega y. Okay. Of course, we will cancel exponential plus omega y, because if you put y infinity, this will go to infinity, the first term. So we have to cancel it. We put only this term because we do not have infinite temperature. So we'll have only y of y equal exponential minus omega y, and the total solution will be exponential minus omega y times sine omega x. We have exponential minus omega y, and we have obtained here sine omega x. We multiply them. The following combination of these eigensolutions represents a solution of the differential equation, okay? Which is the combination here, instead of summation, we put integration. Integration from 0 to infinity of this function, okay, exponential minus omega y sine omega x here, and d omega, and here we have the constant b as function of omega, which is function of omega. Now, if you put the condition, the boundary condition y at y equals 0, which is are the sources at the x-axis, okay, when y equal to 0, it is given function f of x, integration from 0 to infinity b of w sine times d omega. This is the Fourier sine integral, of course, and b of w is given from the above equations where we derive the Fourier transform or Fourier integral. And b of w is equal 2 over pi integration from 0 to infinity f of x sine omega x dx. The problem is finished because we found the solution and we found the constant. Example, in the above example here, assume that f of x, for this example here, for this problem, assume that f of x varies from 0 to pi only, and it is a constant value, 1. Okay, it is like this pulse. So let f of x equal 1 u of x minus pi. No, this is not 1, sorry, it is 1 minus. 1 minus. It is 1 minus u of x minus pi. Okay. So we have two pulses, or u of x, u of x, which is a pulse that starts at x equal to 0, okay? And there is another pulse that starts at x equal pi, and if you subtract them, you will get this pulse, this unit step that starts at 0, and another unit step that starts at pi. If you subtract them, you will obtain a pulse, which is this. Find the solution u as function of x and y here. B of w, we put here, instead of f, we put this unit step function, or this pulse function. So from 0 to pi, it is equal to 1, the pulse. Outside, it is equal to 0. From pi to infinity, it is equal to 0. Sine omega x dx 2 over pi, and this 2 over w. Integration of sine is minus cosine over w from 0 to pi. Okay. So 2 over pi minus 1 over w, and cosine pi, omega pi minus cosine 0. Okay. So it is 2 over omega pi, and insert the minus 1 here, it will be 1 minus cosine pi omega. Okay. So u as function of x and y here, the u. Here we put the value of bw here in this function. So this is the value 2 over pi omega 1 minus cosine times the original function exponential minus omega y sine omega x d omega. So this is 2 over pi, okay, 1 minus cosine omega pi over omega exponential minus omega y sine omega x dw. Let's see the solution along the line x equal y. Okay, this is the line y equal, maybe like this is better, because the angle should be 45 degrees. Okay. U at y equal x equal 2 over pi integration from 0 to infinity. This is a constant exponential. We put here x and x. Okay. Exponential minus omega y sine omega x. Same. Okay. Good, because x equal y here, y equal x. Okay, you can now do, for example, numerical integration and find and draw the result. Okay. Okay, we finished now the Fourier series, and we finished the partial differential equations, and we finished the Fourier transform. And in the next lecture, we will start with the complex functions and complex variables and the residue theorem and conformal mapping and these issues. So we stop here.